Okay, so it's on YouTube now and on Teams. Streaming health is good. Right, look at that problem there. It says the quantity of charge, so the quantity of charge Q in coulombs that is passed through a surface of area 2 square centimeters varies with time according to the equation. So the amount of charge that moves through a certain surface area varies with time, so it's not constant. It varies with time, and it varies according to this formula, which says charge is equal to 4 times the time cubed plus 5 times the time plus 6. This is the formula that describes how the charge passes through a surface area of 2 square centimeters over time. They ask us what is the instantaneous current through the surface at time 1 second. So what's the instantaneous current at a at 1 second? Now we know that this charge varies according to time, right? Through a certain point it's varying according to time. They want to know what is the instantaneous current in terms of time. It is dq over dt. I write it neater. Try to at least it's dq over dt. dq over dt. I keep trying to. There we go. Okay. dq over dt. So current is defined as the amount of charge per unit time, right? The amount of charge per unit time. Now, if you rewrite this thing, it's basically dq dt, the change in current over the change in time. That is, well, the change in charge over time. That is current, right? But you can see this thing as follows. d dt meaning the derivative with respect to time of q. This is mathematically what it means. The derivative with respect to time. Okay? So in order for you to get current, to get the current, you just need to find the derivative with respect to time. Does that make sense? Just a show of hands. I'm just looking here at the chat. Okay. Uh, Asabongwa, I see here that you said that the shared content is blurry. Is it still blurry for you? Before I continue. Okay. I see some delayed responses there. I think it's your Wi-Fi because I see the streaming quality. I'm checking on it now. It seems to be good here on my side, and I have connected to the Ethernet, so it might be your Wi-Fi. Is there anyone else that is experiencing blurriness with the screen?
Yes.
Okay. Then I assume it is either your Wi-Fi or whatever, but I'm going to check quickly because this is just a Teams meeting. I'm not actually streaming on this part. This is just Teams meeting. Let me check the YouTube part. The YouTube seems to be fine. I'm sorry guys that you're experiencing that, but I don't know how to fix that because the YouTube stuff seems to be fine, but you guys are saying you're seeing blurriness on Teams. Anyway, I really don't know what to do here because there seems to be an issue on your side because both my streaming and the Ethernet cables are registering good connections. Can I at least ask, can you see the whiteboard clearly where I'm writing? Like this thing here where I just drew the arrow. Okay, because that is mostly what we'll be working on. So let's just try. If the whiteboard is clear for you, then it's fine. Okay, so we've now defined what the current is. We've found a formula for the current. It is just the derivative of the charge. So we know IT is equal to d dt of q, and we know q is equal to 4t cubed plus 5t plus 6. So this derivative that I'm doing here, or I'm finding, it will give me the current in terms of time. So this will be the current in terms of time. Okay? We want the current at a specific time that we call the instantaneous current. So the current, this is the current for all time. 4t cubed, if we find its derivative, it's just 12t squared. If my calculator is still fine, and this will just be 5. So it is 12t squared plus 5. This formula here is the formula for current at all times, at all t. It's the formula for current at all t, not just for at 1 second or 2 seconds, at all time. Okay, so let's take that formula across. It's 12t, so that formula says current in terms of time is equal to 12t squared plus 5. By the way, guys, if you don't agree with anything I say, just let me know, and we'll try to figure it out together. Maybe I made a mistake, maybe you made a small calculation error or whatever, but we will get there together. Okay, so now I have the current. Okay, what did they ask us? To find the current at a specific time, and that time is 1 second. They wanted it in 1 second. But before I continue, I just need to make sure of something in the question where it says there where t is in seconds. So yes, every t where you plug in t, it is in seconds. So in terms of 1 second, it's 12. You plug in 1 wherever you see a t plus 5. Therefore, the current, the instantaneous current at 1 second. I see a lot of people are just leaving. That's okay. 17 amperes. 17 amperes. So that's the current after 1 second. Okay. Please note this problem. It always comes up as a multiple choice for 2 marks or something. Because first of all, it tells you definition of what current is. You need to know that current is charge per unit time, and it also tests your your application of derivatives, okay, your math skills. 17 amperes. Let's check. 17 amperes. We say here check. We select 17 and we check, and there is a green correct mark there, and they also tell us the correct answer is 17 amperes. Okay, now question number 2, but Let's check something quickly. I want to show you something, or not show you something rather. I want to move to question number two. The thing is, for question number two, the correct answer, the correct option is not provided here. You see, they switched, they changed this problem. They changed this particular problem. Let me read you the problem. It is based on what we did previously. The problem says the quantity of charge Q in coulombs that has passed through a surface of area 2 centimeters varies with time according to the equation Q. This is the same so far as we've done in the first section. Now they ask us what is the value of the current density after T equals to 200 milliseconds. So after T is equal to 200 milliseconds. Now originally it is not 200 milliseconds, it's 200 seconds. But we will work with this. But I do tell you beforehand that the correct answer is not here, the actual correct answer, but I will show you how to collect or how to work out the correct answer. Remember, we already have for this problem, and I'm not going to do it again, we've already found that the current varies according to the formula IT is equal to 12T squared plus 5. This is what we found from the previous problem. I'm not going to do it again. I don't think I need to because everyone paid attention. So, where am I now? Yeah, there we go. So, they asking the current density after 200 milliseconds. Okay, 200 milliseconds. So let's find the instantaneous current after 200 milliseconds. What is 200 milliseconds in terms of seconds? It is just zero point 0.2 of a second. 200 milliseconds is zero point 0.2 of a second. So let's plug that in. 12 times zero point 0.2. You can actually say 0.200. It's the same thing. Square, don't forget to square, and then plus 5. Okay, that is your instantaneous current after 200 milliseconds. Okay, or 1/5. The answer then is equal to, if you work that out, zero point 0.2 squared, that is 0.004, so it's 12 times 0.040 plus 5, which gives me the current at after 200 milliseconds is 5.48 amperes. So this is the current after 200 milliseconds, 5.48 amperes. How do we calculate current density? Remember that 5.48 amperes, so the current after zero point 0.2 milliseconds is equal to 5.48 amperes. That's the current we just calculated, but we want the current density. How do we calculate current density? Current density is equal to the current at that time divided by area. Okay, that's the current density, cross-sectional area. So it will be 5.48 amperes divided by, remember we have been given the area, it's 2 square centimeters. But we can't use square centimeters, we need to use square meters. So it is 2 times 10 to the negative 4 square meters. Okay. Please remember from dimensional analysis how to convert from centimeters to meters. In this case, you just divide by 10,000 to get 2 square meters. I can show you if you want later on, but that is first semester stuff. You should know that by now. 5.48 divided by 2 times 10 to the 4. Normally I don't use the calculator here. There is one there. The reason is because you can plug this in yourself. Okay, I've already worked it out. But if you want to see the answer that I'm correct, 5.48 divided by, that is 2 times 10 to the negative 4, so 0.0004. 1, 2, 3, 4. Is this correct? I need to check something here because this is giving me a different answer than what I have. 5.48, let me clear. Should be fine. 5.48 divided 0.0004. Oh, it should not be 004, it should be 003. Sorry, that's the problem. That's it. I'm wondering why I'm getting this weird number. Okay, so it is then 27,400 amperes per square meter. That's the current density that we should actually get. Now, there is no option for this answer anywhere. Okay, there is no option for this answer anywhere. 27,400 or 27.4 kiloamperes. You can also write it as 27.4 kiloamperes per square meter. Now, as you can see, there is no option for 27 here. They do, however, and I don't know why they do this. Someone made that 25 is the correct answer. It is not the correct answer. The correct answer is 27. The correct answer is 25 only if we use this 200 as 200 seconds under 200 milliseconds. Okay? So we have worked out the actual correct one. So I'm not going to check that one because the correct answer is not there. Question number 3. If you have any questions, I'm going to go to Teams now. I'm balancing my screen. Nothing. Okay, so if you have any questions, you can just ask me. Type it up there. I do periodically check if there are questions. So, an electric field, an electric current in a conductor. Okay, we have a current in a conductor, and it varies with time. This is why we like this type of problems, because you usually assume current just stays constant, but current in actuality fluctuates. Okay, so the electric current I is the electric current in a conductor varies with time according to the expression IT. So the current fluctuates according to, or varies according to this formula: 100 sine 120 pi t. This is the current fluctuates with according to time. There's the t there. The current fluctuates with respect to time according to this formula. Okay, where the current I is in amperes and t is in seconds. It is good that they tell us this because we can't just assume that it is in SI units. They ask us what is the total charge passing a given point in the conductor from when t is equal to 0 to t equals to 1 over 240. Okay, so let's just define out what is 1 over 240. Okay, that is in terms of seconds. So this is 1 second, and this is 1 over 240 seconds. It will be 0, 0 seconds. It should be, let's just work out on the calculator there. 1 divided by 240 is 0, 0.04, 0.04166 seconds. Okay, so I can actually write this as 1 over 240, which is equal to 0.00417 seconds. Okay, so from 0 seconds to 0.004 seconds, so 1,000 of a second, 1,000 of a second later, there is not much time between 0 seconds and 0.00417 seconds. They want to know how much charge passes through a point in that time. You can actually work that out. The total amount of charge. Now, whenever you see a problem like this, they give you the formula, right? If you want, if they give you the charge, if you need to calculate, uh, if they give you the charge in terms of charge, the formula in terms of charge, you need to usually find the derivative, okay, because that's how current is defined. However, if you need to work back from, let me put it simply, to move, this is just simple, it doesn't always work. To move from charge usually to current, you need to find the derivative dy dx. What do you do if you work backwards? If you have the current, but now you need to do the get the charge, you usually find the integral from your start time to your end time. Okay. Just by a show of hands, do you understand this concept? This quick concept that I've just illustrated here. This one. To go from current, okay, to go from charge to current, you find a derivative. But to move from current to charge, you need to find the integration. So by that logic, we have been given the current. We have been given the current, right? And we need the charge. So we need to find the integral. Okay, we need to calculate the integral. So the charge therefore is equal to the integral from T1 to T2 of this formula of the current IT, and of course its terms of dt. Okay, that's all you do. Okay, to get the reverse, remember earlier on, to get from current, to get the current, we had to find dt of the charge. Okay, now we are doing the reverse to get the current, doing the reverse to get the charge. We derived the equation for, we derived the, or found the derivative of charge to get the current, but now we need to find the integral of the current to get the charge. So we have that the charge is equal to that. We can now write it here. Charge is equal to the integral from T1, the start time, to T2, the stop time, of the formula that they gave us for the current, dt. Now what is the start time? 0 seconds. What's the end time? It is 1 over 240. Or you can write there 0.004166667. Okay? And what is the formula that they gave us for the current? The formula for the current we've been provided is 100 times sine times 120 pi t. You need to find this integral dt from 0 to 120, so this makes it a definite integral. Now what is the integral of this whole thing? Let me just add here in red. I'm going to just show you what the integral is. In red, the integral of sine, I'm just reminding you, integral of sine pi t, it can be any constant. The integral of sine pi t, remember 120 pi t is just a constant, 120 pi. Let me just write it in this way so I don't confuse you. This is the general form for an integral. The integral of sine constant times time dt is equal to negative of 1 over whatever that constant is, a cosine pi constant t. This is the integral. Okay, you guys, I'm not going to show you. No, you should already know how to do that from your math class, but it is deceptively simple. The integral of sine is cosine, negative cosine, and then the integral of that inside the brackets is 1 over a. Okay, so here we have the integral. So if we continue the sum in black, we have that 100 is a constant, so it comes outside. Now we get to the integral part. We integrate that sine of 120 pi. So we are left with negative 120 pi underneath that times the cosine of 120 pi t, and we close the square bracket from 1 over 240 from 0 to 1 over 240. Okay, if you plug in where t is 1 over 240 and then you plug in 0, you should get the following answer. Oh, I wonder if I should do it, the upper limit. This integral, let me just rather do the full complete integral so you don't get lost. You can take the constants out. Okay, we're left with 100, negative 100 over 120 pi. I'm just taking the constants out. And then cosine of 120 pi times 1 over 240 minus cosine of 0. Okay, so there we have the actual problem. You can punch that into your calculator. You get that q. If you plug that into your calculator, you get that q is equal to 100 over 120 pi, which is just 5 over 6 pi, 5 over 6 pi, and this is in terms of coulomb. So 5 over 6 pi coulomb. Now if you calculate 5 over 6 pi, you get 5 divided by 6 times pi. That's 5 divided by approximately something around 18 to 20. So basically what you're doing is 5, 6 times 3, comma 1, 4, that. You get approximately, because pi is an irrational number, it doesn't end. So you get 0.265 coulomb. Approximately 0.265 coulombs is the answer. Let's see if we get that. 0.256 coulomb. There is a 0.265 coulombs. And yes, it's correct. We check. Any questions? None. Next question. This is question number 4. Car batteries are often rated in ampere hours. This information designates the amount of what? Ampere hours. What is ampere hours? Does it relate to energy? Is it charge? Is it power? Is it potential energy? Or is it current? What is ampere hours? Because the batteries are rated in ampere hours. So let's understand what ampere hours are. Now, ampere hours can be written as ampere hours, ampere dot hours. Okay? This means it is a unit of charge multiplied by a unit of time. Okay? That is ampere hours. It's charge multiplied by time. Now, what formula do we have that if we have charge multiplied by units? What formula gives you the units of charge multiplied by time? Okay, so what gives charge? Hey, current. Current gives charge, correct? What gives time? Or a unit of time? Time gives a unit of time. So something current multiplied by time is this. But current multiplied by time, if you remember correctly, is also equal to charge. Current multiplied by time is charge. Because current is defined, remember, we define current as charge per unit time. Therefore, time multiplied by current is charge. So, this is a unit of charge. Ampere hours is actually a unit of charge. Ampere hours is a unit of charge. That is what I am saying. Ampere hours is a unit of charge. You can actually work out how many coulombs it is. I will show you now, but we know it is a unit of charge. So let's check. Ampere hours, a unit of charge. The correct answer is charge the battery can supply. So the ampere hours is the amount of charge the battery can supply. You can actually work this out. Q is equal to I times T, right? We've just determined that. That is amperes per unit hours, ampere hours. But you can actually write this just purely in coulombs, okay? 1 ampere hour actually is equal to 3,600 coulombs of charge. So that's 1 ampere hour. Question number 5. A conductor of radius, oh sorry, part of the question is cut off. A conductor of radius r, length L, and resistivity rho has a resistance of R. Okay. What is the new resistance if it is stretched to 4 times its original length without changing its original volume? So the volume stays the same, but its length changes. Okay. We know that the initial formula for resistance is equal to rho multiplied by the length L divided by the area. resistance is equal to the resistivity multiplied by the length over the area. Now, and this is where the area, this is a conductor, it has a radius, so its area, what is the area of something with a radius? Pi r squared. So its radius is pi r squared. Now, if the new length, let's say this is the new length, L prime, okay, the conductor is stretched to 4 times its original length, so it's 4 times L. L prime is now 4 times L, okay. The volume stays the same. V1 is equal, V initial is equal to V final, right? Now quadrupling the length forces the cross-sectional area A prime to shrink by a factor of 4. The volume stays the same. If the volume stays the same and the length is, if the length is 4 times longer, then the cross-sectional, and the volume stays the same, then the cross-sectional area A prime, the new cross-sectional area, must be 4 times smaller than the original one. Remember, let's say area is equal to, or rather, let me write it here. Please remember this. For volume, this is specifically for volume. In order for that volume to stay constant, right? We assume that they state that the volume does not change, but the length changes. Okay, so the length, we know that volume is area times length, right? This is the fundamental formula for volume. It's just the area of the base multiplied by the length. This is volume. Now, if this one, if the length is 4 times longer, in order for the volume to be the same, this one must be 4 times smaller. Okay? Let me write it with a space. Volume is equal to area of the base multiplied by the length. Now they tell us that the volume must be the same, but we've already now made this thing the length 4 times longer. The only way that the volume can be the same is if now we make the area 4 times smaller, because then the force will cancel and the volume will still be the same. So that is why the new area A prime will be 4 times smaller. So we have length prime, the new length, and the new area in terms of the old length and old area. So if we work it out, the new resistance R prime is equal to resistivity, which is a property of the material, does not change, which is the new length L prime and the new area A prime. Okay, but we've already established that L prime is now 4 times the original length, and we've already established that the A prime, the new uh, area, is actually 4 times 4, a quarter of the old area. Right? So 4 divided by a quarter, that is actually 16. 4 divided by a quarter goes into 1 4 times. There is four of them, so it's 16. Or you can just do the old metric. When you are dividing by a fraction, you flip it around and you multiply. So it's 16 rho over L times A. And what is this? We've defined this to be the R. So it's 16 R. So the new resistance R prime, the new resistance is actually 16 times greater than the old resistance. What is the new resistance? 16 times greater than the old resistance. Let's check. 16R. That is correct. You need to be able to do these type of ratio problems. Question number 6. I don't know how much. This one I'm going to flip through quickly because you don't do the Drude model as much. We only do it in solid state physics later on and electrodynamics. Now, in the Drude model of electrical conduction, it is in the book though, the current density is directly proportional to. Okay, so what is the Drude model? What does the Drude model say? The Drude model says current density is equal to N, the number of charge carriers, times the charge of an electron squared, times the average time interval between collisions, divided by M, the mass of the electron. This is the Drude model, times E, the electric field present in the wire. Okay. Now, this is the Drude model. Okay, this is the number of charge. N is the number of charge carriers. N equals the number of charge carriers. Uh, this is the square of the electron charge, or I should rather just say E equals electron charge tau is equal to the average time interval. It's the average time interval between collisions. Okay, basically the mean free path. E is the electric field. That's the electric field. And then M is the mass of the electron. Right. Now we have this formula. This is the Drude model. The question is, the current density is directly, oh, and J of course is the current density. The current density is directly proportional to what? The number of charge carriers per unit volume. Yes, it is directly proportional to the number of charge carriers per unit volume. That is correct. So A is correct. The square of the electron charge, that is correct as well. The product of all four quantities, we haven't listed all four quantities. The average time interval between successive collisions, yes, it's proportional to that. And the electric field present in the wire, bang. Yes, so it is directly proportional to the charge carriers in the volume, the square of the electrons, the square of the electron charge, the average time interval between successive collisions, and the electric field. So it is directly proportional to the product of all four of these quantities. Oh, what did I just do there? Okay, let me just cancel. Okay, chapter 3. There, the product of all four of those quantities that are listed. Okay, and we can check. Yes, the correct answer is the product of all four of those. But you don't need to be so knowledgeable about the Drude model at this stage. You don't do it that much. Now, number 7. Okay, which object below has the lowest resistance? Okay, which object below has the lowest resistance? Now, we know that resistance is equal to the resistivity multiplied by the length divided by the cross-sectional area. Therefore, resistivity is directly proportional to the material, the resistivity is uh, directly proportional to the length, but it is inversely proportional to the area, directly proportional to the inverse of the area. So, which object below has the lowest resistance? All three have the length L, so they are all the same length, so we won't look at that. They're all made out of the same materials, so we won't look at that, so we will look at the cross-sectional area. So the one with the lowest resistance will have the largest cross-sectional area. So the one with the largest cross-sectional area will have the lowest resistance. So let's check the cross-sectional areas. I just need to minimize this so you can see all three. Some more. I just need to show you the drawings. Okay, there they are. So there they are, these three. The first one's so we've already established the one with the highest area, the biggest area will have the biggest area will have the lowest resistance because the resistance is directly proportional to the inverse of the area. Therefore, the higher the area, the lower the resistance. They want which of those three, number one, two, or three? Number one, two, or three? Which one of them will have the lowest resistance? First of all, let's determine what all of their areas are. Number one's area is A. Number two's area is 2A. Number three's area I just need to check there. Is there three of them? The area of the face without a hole is 2A. Area of the hole is A. Okay, so it is. The problem is that it is not constant. The area. The one has an area of a face of A, and then also an end face of A, so its area is A. Okay, but the second one, however, has A, but it ends at 2A. And then the third one has a area of the face without the hole is 2A, but the area of the hole is A. Okay, so its area is also just A. This one's area is somewhere in between 2A and rather 2A is bigger or equal to its area, which is bigger or equal to A. The area of number 2, area of 2. Okay, so this one has an area of just A, this one has an area of just A, but the second one has an area slightly above A, somewhere above A. So I would say object number 2 So the one we said that the one with the highest area will have the lowest resistance. So I am going for object number 2 because object number 1 and 3 have the same area. They say select one. They all have the same resistance. No. Both 1 and 3 will have the same and theirs is less than the resistance of number 2. I will go with B. And then C is number 1. It can't be. D is number 2. E is number 3. Both number 1 and number 3, it can be either, according to me, it can be B or let's just go for number 2. The answer is correct. It is number 2. It will have the highest resistance, the lowest resistance, excuse me. Number 9. Let me check. No questions yet. No questions. Last two questions. Rather 8. Now it's 8. I just need to increase it again. When the length and the area of the cross section are both are doubled, then it's the resistance. What happens to the resistance when we double the length and the area? If we double the length and the area, let's say this is the resistance originally. Okay, it is the resistivity multiplied by the length over the area. But now they say this new resistance R prime. In this new resistance, we double the length, so it's now 2L, and we double the area as well. It is now 2A. These two will cancel, so what you're left with is just rho L over A, which is exactly the same as R. So if you double both the length and the cross-sectional area, then the resistance stays the same. It will remain the same. Check. The resistance will remain the same. That is correct. Number 9, second to last question. Which of the following is true? The resistance of a given material depends on the material's resistivity. Yes, that is true. Let's just go like this. A, that's true, because resistivity is equal to resistance is equal to resistivity times length. Number 9. Resistance is equal to resistivity times length over area. Therefore, A is true. Resistance depends on the resistivity. B, let's say is B true or false? The resistance of a given metal wire increases with the length of the conductor. True. C, the resistivity of a given metal. So this is select one or more. Which of the following is or are true? The resistive of material is true. True. Number 3, the resistivity of a given material depends on the temperature of the surroundings. The resistivity depends on the temperature of the surroundings. Or rather, the resistivity of a given metal depends on the temperature of the surroundings. It is inversely proportional. That is false. Because if you heat up a metal, its resistance increases, not decreases. Or rather, let me just check here. There is 5. Let me come back to C here. I want to check something quickly before I answer C. A, B, C, D, E. Before I come back to C, resistance of a given metal is inversely proportional to temperature. Yeah, this is the problem that I was having. The resistance is inversely proportional to temperature. True. It is true. Resistance is inversely proportional to temperature. The higher the temperature, the lower the resistance. E, the resistance of semiconductors. The resistance of semiconductors is directly proportional to temperature. That is false. That is because semiconductors have negative temperature coefficients. Their resistance decreases as temperature increases because more charge carriers are free. So the resistance of semiconductors is inversely proportional to temperature. And then here we have the final one. That one was correct. I did was correct. It's false. The resistivity of a given metal, that is what the metal is made up of, depends on what the metal is made up of, depends on the temperature of the surroundings. That is false because the resistivity is dependent on what the material is made up of. It's not the resistance, it's the resistivity. That is dependent upon the material itself. Number 10, and final question for today. The color code of a resistor, orange, black, brown, or violet would be, this is for a resistor. I'm going to give you just in case, just so you know the values. The first band is orange. The first band is orange. Then we have another orange. Then we have black. Then we have brown, which is black. Then we have brown, orange, orange, black, brown, and then violet. Okay? We want to know what the resistance would be. So, if the first band is orange, it's 3. If the second band is also 3. The third band is the multiplier, black, 0. Well, no, actually this is just based on a chart, colors. The fourth band is the multiplier, so brown. Brown means times 10 to the 1. Okay, times 10 to the 1. And 10 to the 1 is just 0. Oh, times 10. This is your multiplier, times 10. And violet is your uncertainty or your tolerance, plus minus 1.1%, if I'm not mistaken, 0.1%. Okay, so your fourth band is your multiplier. So you will write this as 330 times 10 plus minus 0.1%. So 330 minus 10 is just 3,300 plus minus 0.1% tolerance. Okay, and that is basically just 3.3 kilo ohm. 3.3 kilo ohm. Check. I know FBB does this a lot where they have to check the colors on resistors. FBB, FDV and PHYV not so much. Okay, so thank you very much for listening. I am done for today. We have done some good problems. Next week we'll do magnetic fields. Okay, all the best. Enjoy the rest of your week. I'm going to stop sharing now. If you have questions, please ask. No questions, so I will stop the recording now or stop the meeting.